Okay, this video is for Stat 210, handout number 6, and it's going to cover pages 26 through 34. All right, let's go ahead and get started here. What we're going to do starting on page 26 here is just working through some examples of a chi-square goodness of fit test. So our first example here has to do with the Boston Medical Center. And this study was centered around the scheduling of elective surgeries over a 2-year period. The scheduling of surgeries is important to the quality patient care and is an important healthcare management issue as well. So in particular, we're going to be looking at the consistency in the scheduling of these surgeries. All right, so the data here is on the bottom of page 26. Go ahead and hit pause on the video and enter the data. You can go ahead and enter the data for the elective surgeries in year 1 and then also the elective surgeries in year 2. So this study was done over a 2-year period and provides information about the number of elective surgeries that are done in each month. So go ahead and hit pause and enter this data. Okay, now that you have the data entered here in JUMP, as I do here, again we have months, and then the elective surgeries. This is the data in year 1, and then this is the data in year 2 here. The first thing I'm going to do is just a couple of things. The first thing I want to do is make sure and keep the data in this order here. So the dates specified, or the months specified in this order. It lists the months starting in September through August, so that must be how their fiscal year is set up. So again, I'm going to right-click on Month, Column Properties, and do a value ordering to keep that order. So this will just take a minute here, but I'm going to have to put them in the order that we've specified. So September 1st is first, and then October. So just give me a minute to put all of these in order. November. We'll move December next. So get those in the right order. That looks correct. September and ending in August. Go ahead and hit OK. And again, that little icon there behind the month indicates that you've specified a particular order. Okay, now to make a simple graph. So that's what we did kind of first here. There's a couple of different ways that we can do that. So here on page, let's see here, page 28 is where I'm getting the output. And also 29 is going to show you how to make the graph. So page 28 there shows you how to get the output. So maybe let's do the output first. I would simply go underneath Analyze, Distribution. The month is what I want to analyze here. And then I'm going to take the number of elective surgeries and put that in the frequency box. And again, I'll be doing the year 1 analysis here. So that's what that data looks like inside of JUMP. Again, if I want to turn it on its side, I can use the little red drop down, just say stack here, and that data is provided there as a bar graph. As shown in the notes, we can also use a line graph to show that information. Okay, so we can do that underneath graph chart if we would like. Okay, so let me show you how to do that. Let's go underneath graph, and chart is actually underneath legacy now. So we're going to go graph, legacy, chart here. We're going to put months in the x-axis. Number of elective surgeries is going to go up here in the statistics box. And then over here on the left, we can connect the points. I need to change that to a line chart, and then it'll change to connect points. Clicking OK will give us that plot that we have there in the notes. Another way to make this chart, I'll just show you that real quickly. It's actually a little bit easier, is using Graph Builder. So let's go under Graph and then Graph Builder. So before I was going underneath Legacy Chart here, but now I can just use Graph Builder. And this is just more of a drag and drop interface for creating graphs. So I can put month down here on the x-axis. And notice the order is correct here because I've specified that particular ordering. The number of elective surgeries is going to go on the y-axis here. And then to connect the dots, I would just select the line up here across the top, which shows a response summarized by categories. Okay, for this particular situation, the expected outcome, well, let's look at what the research question is first, I guess. So the research question, let's go up to the top here. The research question for the Boston Medical Center case study is there enough statistical evidence to suggest that the total inpatient volume was inconsistent throughout year one? Okay, so the research question goes into the alternative hypothesis. So again, total inpatient volume is inconsistent or not consistent. The H0 is how we're going to build the reference distribution, and that is under a consistent situation. Now, if the number of elective surgeries are occurring consistently throughout the year, and there's 12 months, we should expect about 8.33% in each month. And again, where we got that is if we just take 1 divided by 12 here, I'm getting 8.33%. So again, if the elective surgeries are occurring consistently, I should expect about 8.33% in each month. Now, if I wanted to know what the expected number was for each month, what I would have to do is take the total and just multiply that by that 8.33%. So the total here, page 28, is 429 surgeries were done. So if I multiply that 0.0833 times 429 surgeries, I should anticipate about 35 or 36 in each month. So that 35.75, I can actually add that as a reference line on my plot. So that's what I did here on the bottom of page 29. So that value of 35.75 is what my expected number would be if the surgeries were occurring equally. So back here on either one of my plots, I can just click on the y-axis and say add a reference line here in the lower right corner of 35.75. Say add, say OK, and that reference line then will be snapped there. So this is the number of surgeries that I expect in September. I expect 35.75, but you can see we only had about 25. So there's quite a bit of deviation there for September. Something like January, it looks like we're very close to target on January. We're very close to target here in April. The summertime, it looks like we're a little bit higher than expected. And then here in February, we can see that we dipped quite a bit below the expected for February. So again, what this test is going to try to do is figure out how much expected variation I would see for each month. Okay. So what is the expected variation that I would see for each month about this 35.75? And do I have enough evidence to say that I'm outliers against this 35.75 value? Okay, so let's go ahead and do the test. So let's slide down to page. Can go ahead and skip the graph there on page 31. The bottom of page 31 is just kind of showing you what that random variation would be about the 35.75. And it looks like for most months we're actually within that band of random variation, except for February dips below, as we've said above. So to actually get the test done, what I have to do is specify a set of hypothesized probabilities here. And again, this 0.0833 is just the 1 divided by 12. So if they're occurring equally, I would expect about 8.33% in September, October, all the way through the rest of the months. So let's go ahead and go back over into JUMP and conduct this test. So from the red drop-down menu here, I'm going to select Test Probabilities. And I'm going to have to specify those probabilities for each month, which again is the 0.8333. Because they're all the same, I'm just going to copy and paste that in each one of those boxes. And again, the hypothesized probabilities would be set up under the situation of what it would look like if they were consistent throughout the year. I'll go ahead and hit Done here. And again, as we said in class, the test that we're going to want to use is the Pearson chi-square test. So let's go back over here into the notes and finish this example. So the chi-square value here is the 19.25. Again, that is the value that I get if I take all of this information and condense it down to a single number. Again, the degree to which I'm an outlier. The degrees of freedom here is going to be 11 because I have 12 categories. 12 categories minus 1 is 11. Again, 11 of those probabilities are free to vary. The last one will be set, so that's why the degrees of freedom is 11. And then the p-value here, we're going to want to use the Pearson is 0.0567. So let's go ahead and put that in, 0.0567. Make that a little bit bigger so that you can see that on the screen. My decision is to simply ask if my p-value is less than 0.05, then the data is said to support the research question. So here, technically, it is not larger than 0.05, so I'd have to say the data does not support the research question. So what I'm doing here is comparing, is 0.0567 less than 0.05? No. But it is very close to the 0.05 cutoff value. So let's go ahead and write our final conclusion here. Again, there's going to be 3 parts to that. The first is the decision. There is not enough statistical evidence to say. That's the first part. I'm going to go up and just get my research question. I can just copy and paste that right in there as long as I'm doing this electronically. In between pages here. But there is not enough statistical evidence to say that the total inpatient volume is inconsistent in year 1. And that p-value was 0.0567 again. Okay. So technically, if we go back up and look at our graph a minute, the amount of variation there that I'm seeing away from my 35.75 is an acceptable amount of variation. We determined here that there's not enough evidence to say that across these 12 months, my observed outcomes deviate enough from the expected outcomes. Now, that p-value quantity was very close to the 0.05. So what the Boston, if we go back up to look at the origin of this question, what the Boston Medical Center ended up doing was going ahead with making some changes to how the scheduling was done. Okay, so they felt that that p-value of 0. Where's my conclusion at again? They felt that that p-value of 0.0567 was close enough. So in the end, I guess, the Boston Medical Center decided to make changes to their scheduling of these elective surgeries. So keeping these consistent is important because of staffing, for example. All right? They want these to be consistent. They want these to be predictable. Because if they know that they're doing 36 surgeries every single month, then they can plan for that. They can identify how many doctors they need. They can identify how many nurses they need. They can identify how many other staff they need. If the number of surgeries is very consistent, then that's good. So things like September and February are problematic because what are you going to do with the extra staff that's around if February is only doing 20 surgeries? You're going to have to call people and have them not come in because they don't have anything to do. Or what are you going to do in July when the number of surgeries is really high? We're going to have to hire some part-time staff to come in and help us through the summer. So from their perspective, they do want these to be as consistent as possible, at least in terms of staffing. So they felt in the end, again, that improvements could be made here. And they collected data over year 2. So the data from year 2 is after the changes have been made. Okay, so let's go down to page 33 here. Top of page 33. And they gathered data on year 2 here. So now the question is, are the information or is the data that I have from year 2, shall I say, more consistent than year 1's information? So I can figure that out by doing another chi-square test on these elective surgeries from year 2. Now the number of surgeries in year 2 is going to be different than I had in year 1. So when I'm trying to figure out what the expected is, I need to make sure and take this total and divide it by 12. That total is probably going to be different than what I had in year 1. I still want to know whether or not I have consistencies throughout the whole year. So I'm going to have that 8.33% is still going to be the same. So here on page 34, asking for the p-value for this test. So let's go ahead and go do that test for year 2 now. So I don't need my year 1 information anymore. I need to go get the data from year 2. We could make a quick graph of that if we wanted. So again, the shortcut there is to go graph builder. I want to put month on the x-axis again, and I want to put the number of surgeries in year 2 on the y-axis this time. I want to connect the dots. Now that doesn't look as consistent, but that's because I've zoomed way in here. So to make things fair or even, I should probably start this y-axis at 0. So let's go ahead and double click on that and start that y-axis at 0. Expected here is going to be right down the middle here, so I don't know what that's going to be. Well, I need to know what the total is, I guess. So if I know what the total is here, how many total surgeries did we have there? Looks like I got to grab that output quick. So how many total surgeries did I have for year 2? I would do analyze distribution. I would put month there, and number of surgeries in year 2 is going to go in the freak box now. Looks like I had 463 in year 2. So if I want to figure out the expected, I'm going to have to take 463, which is the total, times that 0.0833. So that's about 38.5. So if I want to snap a line again on my second graph that I made for in year 2, that would be at about 38.5. So my reference line for year 2 is going to be a little bit higher than what it was for year 1 because I got slightly more. So this test will figure out, again, whether or not this information is considered statistically consistent or not, relative to the amount of inherent variation in each of those 12 different pyramids or reference distributions that I would compute. Looks a little bit better. February doesn't drop nearly as bad. I still have a spike there in July. September is actually higher than what I expected this time, instead of below. Let's go ahead into jump and finish this test. And again, this is for year 2 here. Make sure I'm using the right output, which it looks like it is. From my red drop down, I'm just going to select test probabilities. Again, from page 33, those probabilities are just that 1/12 again. Copy and paste all those for all those 12 months. Say done here. And now my p-value off of the Pearson here is 0.4293. We are getting this message down here on the bottom that says the hypothesized values did not sum to 1. The probabilities have been rescaled. The reason that's happening is because these technically didn't add to 1 exactly. So Jump just went ahead and rescaled them to make sure that they added up to 1. So that's just a note that you don't need to worry about here. The p-value here is 0.429, I guess, or 4293. 0.4293. Now I do notice that that p-value is quite a bit bigger than what we had before. So before we had something like, what was it, 0.0567 or something. This is not even close to the 0.05 threshold now, which means that we have substantially less evidence to suggest that we have inconsistencies. So is 0.4293 less than 0.05? No, not even close. Okay, so the decision there, I guess, is going to be that the data does not support the research question. All right, data does not support the research question. So again, that conclusion, let's go back up and just copy and paste the one I had before. But that p-value is going to be 0.4293, I guess. So there is not enough evidence. Okay, it's not even close this time, which in reality, this means that the number of surgeries are more consistent. Or technically, we do not have evidence to say inconsistencies exist. Okay, so that's technically that's what we're supposed to say, is that we do not have enough evidence. But the p-value that I got in year 2 is substantially larger than what I had in year 1. So that's saying in year 2, I definitely don't have evidence to say inconsistencies exist. So things are better. I mean, the big picture here is the improvements they made were good. I mean, that's the big picture here, is whatever the changes they made, they improved things. The surgeries, in reality, got more consistent. At least statistically speaking, got more consistent. All right, there's a couple more questions here on the bottom of page 34 that I will let you go ahead and answer. All right, that does it for this video. Thank you.